Let's take a look at Newton's law of gravitation. It states that the attraction force is directly proportional to the product of the masses, in our case, the mass M, the mass capital letter M, and another mass M. And the gravitational force is inversely proportional to the distance between them. So in this case, the direction of R is from left to right. Since the attraction force is in the opposite direction of R, we have to put a negative sign to it. And last but not least, and finally, when it comes to G, G is the universal constant of gravitation. That is actually in your data booklet. E is the gravitational field strength. The gravitational field strength of the mass M is the gravitational force per unit mass. So in this case, you will end up as minus Gm over R squared. So if you were to sketch a graph of E or Fg versus R, this is the graph that you have, because both of them is inversely proportional to negative 1 over R squared. We'll now take a look at how this relates to the acceleration due to gravity, which is your G. So when R is less than Re, Re is the radius of Earth, and rho is the density of Earth. Then in the case, mg is now equal to gmm over R squared, because both the direction of your mg and as well as your gravitational attraction force are both downwards. So they are in the same direction. So from there, we can work out the expression that G is equal to G over R squared. This is actually the mass of Earth. So for the mass of Earth, we can assume that the Earth is spherical. So therefore, we can have 4/3 pi r cubed multiplied by the density of Earth. So with that, we can work out an expression to indicate that G is directly proportional to R. So when R is more than Re, then your G will just be Gm over R squared. So if you were to sketch, a graph of how acceleration due to gravity varies with the distance R, then you will find that this will be directly proportional to R based on this expression, and this will be inversely proportional to R squared based on this expression. Okay, the next question that we're going to look at is why you weigh less at the pole compared to the equator. Before we do that, let's take a quick look as to how the Earth rotates. The Earth rotates from the west to east in the clockwise direction, and the Earth's angular velocity is omega 2 pi over t, and t is the time it takes for it to complete one revolution, which on Earth is 24 hours. So with the calculations, you'll find it's 7.3 times 10 to the power minus 5 radian per second. Okay, there's two reasons why you weigh less at the pole compared to equator. First reason is because that the distance from the center of the Earth to the pole is actually shorter. So since it's shorter, the R is of a smaller value. You'll find that the acceleration due to gravity will now end up being a higher value than as compared to at the equator. The second reason is because the object at the equator undergoes circular motion. So let us take a look at what comprises the centripetal force. First, you have the gravitational attraction force in this direction. Then you have the reaction force acting in the opposite direction by Earth on the object. So from that, you know that the centripetal force is now Fg minus n, which is gmm over Re squared minus n. And that will give rise to our centripetal acceleration, which is m, which in this case, this will give rise to the centripetal force, which then gives rise to mre omega squared. R omega squared is actually the centripetal acceleration. And making n the subject, so n is the force that acts on you, and that will allow you to find out the acceleration due to gravity that you experience. So making n the subject, you'll be gmm over Re squared minus this, and from there we can come on. And from there, we are able to derive the final expression, whereby you can see that this was originally the acceleration due to gravity at the equator, but you now have to subtract away the centripetal acceleration. Hence, that's the reason why the acceleration due to gravity at the equator is lower.